Hello everybody. I am Atef Hamada from University of Olo. Today this is the second presentation for me. In this conference, I presented the first one about flash annealing of steel, high strength steel, but this second presentation about fatigue of ultra high strength steel. As you can see here, this work conducted at University of Olo. I'm coming from there, from Finland, and the weather here, like as you know, you can feel very hot comparing to Finland. So now we are not in good mood. But anyway, we should live here for five days in Croatia. I like this country, very nice country. I could recommend you to go to city center, very nice place, many squares there, and take dinner. This work titled Comparative Study of High Cycle Fatigue and Failure Mechanism in Ultra High Strength Steel, chemical composition, chrome, nickel, molybdenum, tungsten, manganese, vanadium, low alloy steel. This work cooperated, co-authored by Atef Hamada, myself, Mohammed Ali, Sumit, and Matias Jaskari. Matias behind you, you can look to him. This group from Finland, University of Oulu, Kurt Salat Institute, our group Future Manufacturing Technology. So we are mainly our work, our study about thermomechanical of steel, additive manufacturing, flash annealing, Gillespie simulator. So also we are focused on fatigue, and we have good collaboration. So if you are interested, we can talk together and make good collaboration. Okay, at the same time, we have this work also cooperated with Tarek, Allam, Professor Rose from Fortune Center in Germany, Ulish, and also Dr. Eissa and Taha Mattar from Egypt, because this steel is casted and melted in Egypt. And then this was part from program PhD from Muhammad Ali, and so Matias, he conducted the fatigue test, and Sumit, he made some microstructure, and Atef Hamad, myself, I conducted fracture analysis and written the paper in future would be published, can be in this proceeding or journal, but let's see. Okay, first, just to make short introduction for 10 minutes about low alloy ultra high strength steel. I adjust the time here, so we'll ring after 12 minutes. Okay, so don't worry.
Okay.
So just short about what we should know about ultra high strength steel, low alloy. This steel already made, designed, and produced to get yield strength of 1 gigapascal, and strength will be extremely high strength, 2 gigapascal, and high toughness. This steel mainly should be microalloying with some vanadium or tungsten, chromium, nickel to get like some precipitation, and mainly the structure should be martensitic or magnetic or both. So we have this steel different based on the design. So the first steel of ultra high strength steel category will be like maybe martensitic steel, the first one, and this is our steel, and magnetic steel, second. Third steel will be like dual phase steel. This consists of soft ferrite and hard martensite phase. Fourth will be like precipitation hardened steel to achieve high strength through formation of fine precipitate during aging treatment. Come this transformation, go to the banana curve. Okay, I think most of us know about banana curve. Okay, now we focus on this area, this ultra high strength steel in red color. So that mainly this steel will be like for dent intrusion resistance. It's mainly a resistance for local deformation. For example, during accidents for the car, we could normally use it for automotive panel, and also for military defense structure, because the high strength should be, yield strength will be like almost like 1,000, 1 gigapascal, and the strength should be 2 gigapascal. This is the, okay, we not talk about second generation or third generation, but now talk about the strength of our steel. This is banana curve. I think all of us has the idea about this banana curve. Okay, now our study mainly for design ultra high strength steel with target strength 2 gigapascal, to also study the positive impact of oxide cleaning, because this steel melted and cast in Egypt. But now our friend, he studied PhD in Finland, and he got this material in Finland and make processing in Finland, but he didn't make electroslag remelting to clean the steel from non-metallic inclusion. So now we want to study the effect or impact of cleanless on our steel and fatigue behavior of the steel. Part of this work published about in material science during A, but here we studied thermomechanical processing and physical modeling and hole deformation for this material. So, okay, now we have second part. Look to just 2 minutes or 3 minutes about design consideration of our steel based on chemical composition. You can see here now we have two steel, ultra-high strength steel, steel A and steel B. We have different in carbon content, different mainly in nickel content, and also select 2% and 4%. Tungsten almost the same, and also we have moly about the same. But okay, carbon content, because this from this during forging and processing of this steel A, mainly the structure will be martensite, polymartensite, plus 5 maybe like few percent of retained austenite, but still be because the low carbon and high nickel, this steel will enhance bionic transformation during air cooling. So that's why we have here carbon 0.3 and chromium. Okay, chromium almost here, just also here higher than the second steel. Nickel strong carbide former. We have moly and vanadium and tungsten both, but mainly the difference will be like in carbon content and nickel content, because this steel will enhance polymartensite. This will be have almost dual feed structure martensite plus 50% binite. Okay, this is a thermocalc from the first steel using TCF database. You can see here, okay, you have like different carbide to enhance the strength and yield strength, mainly tungsten carbide, vanadium carbide, niobium titanium carbide, and also mainly strike will be like here austenite. So during air cooling will be like mainly martensite. Okay, this is also ABCD for the both steel after forging and the air cooling. We have also almost the normal ABCD can't identify between ferrite and martensite. So normal will be like we select index BCC for both steel. So this one will like BCC mainly and ABCD, but we have like green, some green, small green particle, this retained austenite. But of course, our colleague like he make like color etching to recognize binite from martensite. So and this one, this CTT diagram by GeoMat Pro software to see like the martensite transformation, MS and the MF, and binite here you can see using high carbon, the MS will be like shift to the low temperature. So we here okay, this theoretical CTT diagram, but actually we can see now from the result. Of course, we started fatigue test under force control with the stress ratio R-1 using electron model 8800 control. And also we have this machine, very strong machine with load capacity about 250 kilonewton. After that, we start, of course, we should study the mechanical properties using quasi-static, using Zewitt machine, strain rate 10⁻⁻3. And we studied microdentation hardness to see the cyclic softening and hardening, the effect of soft hardening, cyclic deformation on the material, two material. Of course, oh, sorry, that, okay, I didn't change this, this is my mistake. I'm sorry, don't look at this one. Okay, this is a sample geometry. We have used it in fatigue test, ASTM E44666007. In Forschung Center in Germany, we have used this new microscope. It's called RoboMate 3D. This RoboMate, this new technique to detect the non-metallic occlusion or any defect in cast material of material using robot mate. This make like polishing, mechanical polishing. Every, for example, you can make order for the robot like 10 make mechanical polishing 10 micro. Then make take picture and again back robot. Make 10 micro mechanical polishing and again take this just after 72 image will make reconstruction for the image and he give you 3D dimension for non-metallic occlusion. It's very interesting, and this new microscope this in ULH in Forschung Center, and you will now I will show the I will present the result of RoboMate to see how can use this material, this technique to detect any defect in the material. Okay, this is the microstructure of the steel A with high carbon and the low nickel, and both like after forging and air cooling. We have now the microstructure mainly here, fully martensite, but this is still B because high nickel, low carbon give like almost here martensite, and we have broken last martensite is here, this by night, and this martensite from the last morphology because you know it's so difficult. Okay, if you are experienced in steel microstructure exactly from bainite and martensite, so difficult to organize between them. So we need like okay color etching to exactly to calculate the volume fraction of martensite and bainite for this steel. But this is okay. This poly martensite and just we have 5% of retained austenite. Okay, this is the mechanical properties of this two material. You can see here the fully martensite. We have like high strength, almost like 1.8 gigapascal with ductility about 12%, but still be including bainite. Of course, to be some softening. We have like yield strength can 1200, yield strength still quite high, and but more ductility. Here we using micro indentation hardness. We can see this loading and loading curve, and from it just before fatigue to know what is the micro indentation hardness. It's HIT using Berkovich indenter. We found, of course, for steel A because like hard matrix, we found steel A about the indentation hardness 7.7 gigapascal, but for steel B, including bainite, 50% bainite, so the hardness like decreased to 5.24. So this is the mechanical properties using tensile test and micro indentation hardness for both steel. Now to come the fracture to fatigue SN curve, we found, of course, this is the polymartensite steel A. You can see like the fatigue limit is higher than by steel martensite bainite. This is about fatigue limit here 550 megapascal, and this one 500 megapascal. Of course, this one we should focus on this one because our colleague Matias is familiar. He normally beat this fatigue limit, this point about 3 times, 4 times, 5 times to be sure. Now here there is no fracture to be sure this fatigue limit without failure at this stress amplitude. So of course, with increasing stress amplitude, of course, fatigue life will decrease. But anyway, here we can see the steel A with fully martensite structure show higher fatigue life of that steel B, including martensite and bainite 50%. Now we come to the fracture analysis. Of course, it's 12 minutes now. 12 minutes. But just give me 3 minutes more. Okay. But now
we don't get any question, yeah? So
yes, no problem. I think Sir next.
Don't discuss with me. Go ahead.
Okay. Now we come to the fracture analysis. We can see here the fracture initiation, this region, and here crack propagation, this and this overloaded region. At high magnification, we can see here we found some non-metallic inclusion with dimension 150, big inclusion, and this make fatigue initiation region. And unfortunately, this particle come on the surface, which make higher on the surface, and we know we have higher stress concentration on the surface. For steel A, steel, okay, we have done EDX analysis to see what is the chemical composition of non-metallic inclusion. It was mainly about silicon manganese oxide, because here we have oxide here, this particle, non-metallic, and this oxide, and we have here manganese and the silicon, so it's mainly manganese silicon oxide. Of course, we in the middle of the material, we found also some non-metallic inclusion here, and also this big slag come also manganese, iron, manganese silicon oxide. Because this, as I told you, this not clean steel, but still the fatigue life, fatigue strength, it will still high 550. For steel B, we have the same problem. We have also non-metallic inclusion in the surface. Yeah, and here the crack propagation region, and here overloaded. But also we found here in the middle iron oxide, but doesn't cause crack initiation. The same we have done EDS for the steel B. We found chemical composition mainly silicon manganese oxide. But I want to go to, okay, this to show, okay, we found, okay, make chemical polishing to say, okay, inside internal the material, we found here edge crack, and this, anyway. Sorry, this is my wife. I'm sorry.
Yeah, your wife is telling you that.
I'm sorry, I stopped. Okay, and here we have edge crack, and we have also in steel B, we found also some crack through slip band, 45 degree. Okay.
Oh,
No, we stop this one. Just I want to show. Okay, this is the result of road mat. Okay, this road mat is general view from steel A. We found here, this is the general map at low magnification, and we found here inclusion I and inclusion I. And after 3 dimension at 72 section, we found this is the shape and dimension of the non-metallic inclusion in steel A. You can see here, this one, big inclusion, and this is the main reason for the crack, fatigue crack initiation, is using mid-map Pro. After fatigue, we also, this before fatigue, we found, you look, still A, show like high hardness, okay? But after fatigue, cyclic fatigue, we found this is still makes some softening because shift like this to the right hand, and this is still B, make hardening, okay? So that shows, and you can see them, for example, this still A, the value H hardness is decreased, drop from 7.7 to about 5.6. This means there is softening in steel A, martensitic, but still B, including binite, softer. No, during cyclic fatigue, there is hardening in the cyclic behavior, and it's hardest from 5.2 to 5.4. So this softening and hardening due to the phase destruction. What else? Okay, this is the result, the conclusion. Okay, we found non-metallic inclusion because this non-clean steel acts as stress concentrator for localized cyclic plastic deformation. It is the main reason for fatigue crack initiation. And I recommend for you to use this microscope if you want to detect any defect inside the material, a cast material, or even you have like additive manufacturing material. Use this rope mat 3D microscope to make different section and make reconstruction for the defect and give you some static information about the defect. And thank you so much. In Finnish, it's called Kiitos.